I'd like to turn it over to our Vice President, Michael Grenet, who will give an introduction for tonight's speaker.
Okay, thank you very much, Dan. It's my pleasure to introduce to you Dr. Willoughby and her alter ego, Emily Willoughby. It's very rare to meet an accomplished scientist who is also a talented artist. By day, Dr. Willoughby is an instructor and researcher in the Department of Psychology at the University of Minnesota in Minneapolis. Recently, she was awarded her PhD degree in psychology with a specialty in personality, individual differences, and behavior genetics. She's the author of 5 scientific papers and author on 4 others. These have been cited 804 times, according to Google Scholar. She has won many awards for her research, including 2 from the International Society for Intelligence Research. She is used to being in front of an audience, presenting research projects at 11 conferences, not including posters. This is very impressive, and yet is not why you are all here with us. We want to hear from Emily Willoughby, the paleo artist. And as an artist, she's really an impressive suite of accomplishments. I hope you visited her website to see some of her work. She has pursued art as an avocation since childhood and identified artists such as Gregory Paul and Kay as influences since she was in high school. Approaching her art with scientific rigor, she has visions and published art since she was a teenager. Her work appeared in scientific publications in paleontology. She's editions from 8 museums and has co-authored 1 book, authored 7 science popular artists, been lead illustrator for books, and has featured in scores of other book artists and blogs. In 2017, she was featured in a book, The Art of the Dinosaur, and, as I quote, one of 9 of the world's most technically and aesthetically accomplished artists today. So watch for her next soon-to-be-published book on paleo art. Without further ado, please unmute your microphone, and Emily, a very warm welcome. All yours, Emily.
All right, thank you very much. That was a lovely introduction. I will do my best to live up to it. So I'll be talking about the science and art of paleontological illustration. And for those of you who are somewhat familiar with my work, you probably know that I definitely have a strong focus on feathered dinosaurs, and true to form, that will constitute the majority of what I'll be talking about today. But hopefully that'll be interesting enough to everybody. Okay, so just as an overview of what I'm hoping to cover today, I'll just start with a definition of paleo art and why it's important. Like, why would we want to focus on painting dinosaurs as opposed to all of the other, hundreds and millions of possible natural subjects? And then we'll talk a little bit about the actual process involved in creating paleo art with some specific examples and how we can use fossils and skeletons as a kind of a launch pad for creating paleo art, but how so much of what goes into it comes from the research and inference that we have to make from evolution and biology and many other sources. And I'll end with why I personally think that paleo art is especially important, not just to paleontology, but to science in general and to making predictions about how our natural world actually works. Okay, so what is paleo art to start with? Well, the definition may vary depending on who you ask. I know that invertebrate paleontologists put a lot more emphasis on invertebrate paleo art, of course, but as I am a kind of specifically a dinosaur paleo artist, I'll just be talking about dinosaurs today. So paleo art of all types is a category of scientific illustration that focuses, of course, on prehistoric life. And it requires an understanding of research as well as basic evolutionary, anatomical, and biological principles, as well as artistic techniques. And even though it's based in research, and it's important to attempt at least to reconstruct your subject as accurately as is possible, there is still plenty of room for creative expression and interpretation and speculation. In fact, it's almost impossible to create a piece of paleo art that does not involve at least a little bit of reasoned speculation. So there's plenty of room for creativity in the creation of paleo art. So why paint dinosaurs opposed to anything else? Well, paleo art is important in a number of ways. For one thing, it's really the only means of communicating the actual life appearance of dinosaurs to the general public. And that includes skeletal mounts as paleo art. I guess some people might consider that to be kind of stretching the definition. But I think it's fair to include the creation of skeletal mounts of dinosaurs that appear in museums, as well as the presentation of fossils more generally, as requiring some amount of interpretation, right? We have to understand how a dinosaur held its body, how it might have moved, the range of motion of its limbs or its neck, in order to put together an accurate skeletal mount in a museum. So paleo art is incredibly important to attracting the general public to paleontology. It facilitates an interest in dinosaurs and other extinct animals, and in large part, it drives people to the museum, right? People who pay to see dinosaur skeletons and their representations in museum murals and artworks and so on. They form a large part of what funds paleontology as a science. And so it's important for all of these reasons to disseminate science to the public, to fund paleontology as a discipline. But I think it's also important for another reason that's a little bit, less down to earth, I suppose, a little bit more kind of interesting, in the sense that we kind of have an obligation as paleo artists to represent these animals as they might have actually existed and kind of pay respects to them in a way. So this, for example, this is an illustration here of a dinosaur called Meilong. And Meilong is a small troodontid that was probably covered in feathers. And it's an extremely unique fossil, and it also represents an individual. We have to keep that in mind sometimes. Another example, this is Talos, a relative of Meilong, another small troodontid. And the entire genus and species represented here is known from only the holotype fossil. So everything we know about this entire genus of animals comes from just a single representation that just happened to fossilize for us to find. And so everything we know about it comes from this fossil, but we also have to keep in mind that this fossil represents a single individual dinosaur. The specific fossil even has the individual had a partially broken toe that it had healed when it died. And so part of what I think is important about paleo art is trying to capture the unique individual represented by a fossil. And in doing so, I think we can add a lot to the public's interest and understanding of dinosaurs. A lot of little kids get into dinosaurs because, they're really huge, they have gigantic teeth, they're cool, they were probably loud and very imposing sights. But we have to remember always that they are not movie monsters, right? They're not mythical creatures that lived in some mythical land. They are animals, just like animals alive today. And to that end, we can try to represent them as a wildlife artist would represent, a wolf or an eagle or anything else. And I think that capturing this sense of individuality and the realism of the animal as it existed in its environment can really help to deepen the public's experience of dinosaurs. Because even though they are cool and they are ferocious, dinosaurs are often also beautiful. And I do my best to bring out that sense of wonder and fascination in my own art. So that's why I do paleo art. Okay, well, next we'll talk a little bit about the actual process of creating paleo art. And the easiest place to start, as always, is just with the fossil, because almost everything that we know about extinct dinosaurs comes from fossils. So here is one of the two known complete specimens of Mei Long, as a little feathered troodontid. This is one of the most beautiful fossils, I think, in all of paleontology. It's preserved fully three-dimensional, and it comes from an extraordinary preservation environment of early Cretaceous Liaoning China. So it lived about 125 million years ago. And both of the known specimens of Mei Long are they actually are preserved in a very similar position. And the position is that the animal has its little snout tucked behind its arm, and it's curled. It's got its tail curled around its body, much like a bird would actually be sleeping. So the name Mei Long means sleeping dragon. So one of the best places to learn how to start reconstructing dinosaurs is from the fossils themselves. And fossils like Mei Long can give us an opportunity to draw over the skeleton and kind of see how the animal emerges from just this beautiful specimen. So when we see how the bones fit together, we can more clearly now see that the skull is very large for the size of the animal, and overall the animal was only about half a meter long from tip to tail. The fact that the head and the eye socket are so large means that this animal was a very young juvenile when it died. So we can see by layering the skin over the skeleton, imagining the meat and muscle below it, now we can start to see a real animal emerge from this fossil. And at this level of analysis, Mei Long looks like kind of a big reptile that you might have seen, in old dinosaur movies and books and so on. But we happen to know from a huge amount of evidence that Mei Long and the entire family that it belonged to were almost certainly covered in feathers. And we even have an extraordinary amount of information about how these feathers were probably arranged, what they were for, how they evolved, and even in some cases what colors they were. So Mei Long is one of my favorite examples, but nothing quite compares to Microraptor. So Microraptor will be a major focus of all of the points that I'll cover in this talk. This is another one of the most beautiful fossils, I think, in all of paleontology. This is the specimen of Microraptor Gui, described in 2003. And so even though this specimen is not preserved in 3 dimensions like Mei Long, this one comes fully articulated on a slab, and it also happens to preserve the imprints of integument, or the body covering of the animal. In this case, you can see that it is covered in feathers. And if you look closely, you can even see that the feathers are, they bear a striking resemblance to the feathers of modern birds. So in this case, we're not just talking about, shaggy proto-feather filaments. We're talking about an animal that might have looked very much like a bird and might have been using its feathers for the same thing. You can also see on its legs, it has feathers there as well. So if we draw over this fossil, we can more clearly see how the feathers map onto the different parts of the skeleton. And now you can more clearly see that the feather imprints preserved on the legs are almost as long as those preserved on the hand. Now, if we layer this guy up with skin and fat and muscle and so on, now we can see something emerging from this fossil that looks kind of like a plucked chicken. But unlike a chicken, it has these huge claws on 3-fingered hands. It has teeth, and it has this extremely long bony tail. So even though this dinosaur has a lot in common with birds, it was definitely not a bird. If we layer then with feathers, we can see a little bit better what they would have possibly looked like in real life when the animal, well, maybe was not alive per se, but was very recently dead at least. And you can see now that the hands were very much like a bird's wing in light, except it had these huge thumb claws that would have been pretty mobile at the jutting out from the wrist. And we can see that the feathers on the legs are also asymmetrical, and they are also adapted for something at least approaching flight or gliding. But in paleoart, we're usually not concerned with representing the animal dead, right? Although sometimes, of course. But we're more interested in thinking about how the animal actually moved around in its environment. How did it hold itself? How did it position its legs and its tail? So there's a whole genre of paleoart of incredibly talented, devoted artists whose job is to make these skeletal reconstructions from fossils. And this is one of the very few that I have attempted to make here. But we can see that Microraptor, unlike most modern reptiles, it would not have had its legs sprawling out to the side. It would have not been crawling around on its belly like a lizard, but it held its legs beneath its body like a bird, and it held its spine probably mostly horizontally when it was moving about normally on the ground. If we actually look at the features of the skeleton down to the individual bones, we can see some interesting things. So, for example, Microraptor had a furcula, right? Better known as a wishbone that you're probably familiar with in chicken dinners and so on. But Microraptor also had a very shallow breastbone, unlike a modern bird with a huge enlarged keeled breastbone. And so Microraptor might have been doing something approximating gliding or flying, but it was probably not flying like a bird flies today, because otherwise it would have features that we do not actually see here. So Microraptor is an excellent example of a type of dinosaur that, even though it might seem kind of bird-like at first glance, it really is completely unlike anything that we have today. It's not a bird, and in fact, it's kind of only a cousin to birds. Birds did not evolve from the group of dinosaurs that Microraptor belongs to. It is actually more closely related to Deinonychus and Velociraptor. It is a dromaeosaur. And so with the feathers overlaid, we can start to see how complicated paleoart can get, because these voluminous wing feathers, especially the ones on its legs, that are so neatly and perfectly preserved in the fossil, are very strange structures. So what would Microraptor have been doing with these huge fluffy trousers, right? It looks like maybe it would have trouble running around and walking normally. And so part of the point of paleoart is trying to put all of these pieces together with totally different levels of interacting analysis to construct an animal that actually looked like it could have been alive, right? So this is one illustration that I've done of Microraptor, and it serves as a good example of how much research sometimes goes into a single piece of paleoart, and how usually a single fossil is not very sufficient to draw something that looks like a real animal. In this case, this single picture of Microraptor took inference from quite a variety of different research, right? So first, the description of the specimen is the first kind of foundational level to understand the skeleton and the feathers that are suggested by these beautiful imprints. Second, we have to model some kind of behavior. What is the animal actually doing? In this case, it is eating a fish. Now, we happen to know something, thanks to Denver Fowler's 2011 study on raptor prey restraint, about how a dromaeosaur dinosaur might have actually held its food or its prey when it was ripping into it. And we'll have some better examples of raptor prey restraint a little bit later. But basically, there's some evidence to suggest that it might have held the prey animal down with its foot and putting its weight on that enlarged second claw, and then ripped meat out of it with its mouth. Third, the color of Microraptor is not just on a whim. It is actually informed by some remarkable research and technology that has actually been able to identify fossilized pigment organelles in the feathers themselves. So there's one specimen of Microraptor where the feathers are so well preserved that researchers can look at the structure of them under a microscope and see the actual shape of these tiny little organelles that would have produced color in feathers. And they concluded that Microraptors, these organelles called melanosomes in Microraptor, are arranged in a multiple layered kind of structure, and that the shape of them is extremely similar to the same organelles in the feathers of birds like starlings and grackles and crows. In other words, Microraptor might have been colored like a crow or a grackle. So iridescent, shiny blue, black. So fourth, the actual research paper that this illustration was made to accompany found fossilized gut contents in the specimen's stomach. And so we happen to know with absolute certainty that Microraptor was eating the specific genus of fish, right? So incidentally, several other studies have found different kinds of prey items preserved in different specimens of Microraptor, including an early mammal as well as a smaller bird. So Microraptor was eating a number of different things, including fish. And then, of course, there's the environment. And I often find the accurate representation of Mesozoic plant life to be one of the most challenging aspects of paleoart. And I am definitely not a botanist, and when I'm trying to make a scene like this, I really have to hit the books. So we do happen to know that in this early Cretaceous Chinese environment, there were plants that were like semi-aquatic type plants, including Archaefructus and Leafructus. We also know that algae blooms would have been extremely common in ponds back then, because algae blooms are extremely common when there is a lot of falling volcanic ash. And most of these incredible specimens that come out of Liaoning are preserved by volcanic ash. So we know that algae blooms were likely to be quite common. And then, of course, there's ginkgo, which is possibly the most popular of all plants to depict in paleoart. But it's worth pointing out that the type of ginkgo around back then was not the kind that we have today. So today we have ginkgo biloba with those very distinctly shaped kind of triangular leaves. But the only ginkgo that would have been around in early Cretaceous Liaoning is called ginkgo apodes. And so ginkgo apodes has these very distinctive lobe-shaped parts to the leaves. So in sum, this single piece of paleoart comes from, you know, a huge number of different studies and the inferences that they afford. So we also in paleoart have to understand a lot of things about how the animal is actually using its body. How was it able to move? We see that, you know, Microraptor has these big clawed hands. Well, how far could it move those hands? Would these giant feathers on its wings have been actually useful for flapping if it can't move its shoulder past a certain angle, right? So these are the things that we need to understand that kind of goes beyond just the fossil itself. And part of what comes from this is this kind of complicated set of inferences that we need to figure out. And one example that is very important to my art is the presence or absence of feathers, right? What kind of integument did a given dinosaur have? Because if we had a fossil like Microraptor for every type of dinosaur out there, well, we wouldn't need to struggle so much with this. But the vast majority of fossils that we have do not preserve feathers or scales or anything else. So we have to use a kind of inferential reasoning to figure out what kind of feathers, if they had feathers, or what kind of scales, if they had scales, a dinosaur was likely to have. So we can see this is a cladogram that is based on a paper that looked at all of the known preserved integument across all of these different groups of dinosaurs. And so we can see here at the bottom, these groups down here, which includes ornithese modern birds, that we have relatively advanced feathers, at least in some fossils in these groups. So that would include things like Archaeopteryx, as well as dromaeosaurs like Deinonychus, Microraptor, and Velociraptor, as well as a few other groups like oviraptors that I'll talk a little bit more about later. But then we can also see some kind of interesting and strange things if we look further up here on this chart at these groups of dinosaurs that are much more distantly related from birds. So we have evidence of primitive filament type feathers from animals like Psittacosaurus and even Heterodontosaurs, which are very, very distantly related to birds. And even in tyrannosauroids, we have slightly more complex feathers. And so what is this kind of chart useful for when it comes to paleoart? Well, this is an example of something called phylogenetic bracketing. And this is a method of biological inference that we can use to sort of assess the likelihood of an unknown trait in groups of organisms based on their position in a phylogenetic or evolutionary tree. So in other words, you can be about as certain that a newly discovered dromaeosaur bone belonged to an animal that had feathers as you would be in assessing an extinct feline would have been covered in fur, because all cats have fur, and all dromaeosaurs that have been found with any kind of preservational integument had feathers. So this is one of the most useful tools in reconstructing the life appearance of dinosaurs. Just as an example of some of the unusual dinosaurs that are unrelated to birds, where we found evidence of some kind of feather-like structure, Tianyulong was a type of heterodontosaurid that had, the fossil was found with imprints of these kind of long quill-like filaments extruding from its hips and its back, like that. And Coulindrodromeus is a basal neornithischian. So when an animal like this is found with feathers that is relatively near the root of a big group, then it becomes slightly more likely that that any member of that group would have also had feathers, or something similar to these filamentous structures at least. And then Psittacosaurus was a small ceratopsian that also shows evidence of kind of similar quill-like extrusions from the back and the tail. So Psittacosaurus means that it's possible that a variety of different ceratopsian type dinosaurs also may have had some kind of integument like this. And in fact, feathers might even be the ancestral condition of dinosaurs in general, which is kind of an amazing thought, that it's possible that all of the dinosaurs that we know have scales may actually have evolved from an ancestor that in fact had feathers. So this is an example of a feathered theropod that was once considered to be a megalosaurid, but that has been debated. And currently, I think that nobody really is quite sure what exactly Sciuromimus really was. in part because it was a very young juvenile. And like Meilong, it had a big head and a big eye socket, and it was very small. So Sciuromimus means squirrel mimic, and it's named after the extremely long filaments that were found on his tail. And so these kind of filament hair-like or fur-like structures are much more common the further away you get from birds. So it also has turned out that the ancient ancestors of the T-Rex also have positive evidence for feathers. So this is Dilong paradoxus. This is a basal tyrannosauroid that was very small, and it had evidence of the same kind of monofilaments or hair-like feathers that Sciuromimus had. Now this dinosaur is technically not a tyrannosaurid, it's a tyrannosauroid, which means that it's a little bit further out from the familiar tyrannosaurs like T-Rex. And Dilong was also very small. So a lot of people would say, well, you know, this animal was, you know, just a few dozen pounds. It's a lot easier for a small animal to be feathered than a big one. But shortly after, we found evidence of a much larger tyrannosauroid called Eutyrannus here in the background, which also had these kind of long filaments, and it had them all over its body. It appeared to be a very heavily covered, furry, feathery dinosaur. In the front here, this is a type of Oviraptorosaur that we also know for sure was feathered. And this animal had much more advanced type of feathers than Eutyrannus. But nevertheless, Eutyrannus is quite large. It's not quite as big as T-Rex, but it is still on record as being the largest dinosaur that we know of for sure that had direct evidence of feathers. So as you can imagine, these findings have led to a great amount of speculation about whether the big T-Rex himself would have been feathered. I think it even turned into a kind of paleo-art meme for a little while that T-Rex would have been feathered. But in fact, this is an example of a case where we have direct evidence instead of scales. And these come from several different specimens of T-Rex that have preserved different kinds of scales on different parts of its body, including the neck, the back, the tail, the feet, the shoulder, and a few other places. So what this means is that even though T-Rex may have evolved from a feathered ancestor, it either secondarily lost those feathers, or if it has any remaining feathers, they would be too small and sparse to be preserved at this point. So even though phylogenetic bracketing for things like feathers can be very useful to paleoart, it cannot supersede direct evidence, which we do happen to have in the case of T-Rex. When it comes to the smaller feathery type of things, though, we have evidence now from dozens of fossils of feathers in theropods that were related to Oviraptorosaurs and dromaeosaurs and triodontids and other type of Maniraptoran dinosaurs. And so we talked briefly about the color study of Microraptor and the preservation of these tiny little organelles that produce pigment. But what about everything else that does not have such unique preservational conditions? Most of the fossils that we know were feathered, either through direct or indirect evidence, have not had color studies of this sort. So we have to move on to a different level of inference when we are trying to figure out the most likely life appearance of feathers in these dinosaurs. And so some areas of inference that we can use are the structure of the feathers themselves, which is itself informed by our evolutionary bracketing, as well as things like diet and lifestyle. So many of these kinds of feathered dinosaurs that I've showed you so far like Sciuromymus and Sinosauropteryx, have very simple feathers. Some others, like the Dromaeosaurus Sinornithosaurus, have slightly more advanced feathers. But these feathers are still kind of unique in that they had absolutely no flight capabilities to them. And so, we have to figure out, well, what are the limitations of coloration imposed by feathers of different structure? And then what would have such feathers been useful for? So why would an animal like Sinornithosaurus have feathers that could not interlock for an airfoil, but were still considerably more advanced than the hair-like monofilaments that existed before it? So some options are thermoregulation or display or camouflage. So the coloration of dinosaurs is one of my favorite areas. We have had color studies that have been conducted on some dinosaurs that had more primitive feathers as well. So in the case of Sinosauropteryx, this is little Compsognathid. Here's a picture of the fossil here. You can see the line of preserved feathers that go down its head and back and all the way up the tail. And so color studies of this animal have revealed it to be kind of this russet reddish color on most of its body with a lighter underside, and also a ringed tail, much like a raccoon or a lemur. We can kind of even see some evidence of the rings just in the pattern of feathers on the fossil's tail. Sometimes it turns out that dinosaurs actually were colored very similarly to modern birds. And this is an example of a dinosaur very close to the bird line, but not quite a bird, called Anchiornis. And a color study on Anchiornis revealed it to be black and white with a pattern of kind of like spots and bars on its wings and tail, as well as this incredibly interesting reddish crest. And so it's kind of tempting to imagine that a woodpecker style coloration would have evolved convergently multiple times, possibly for a similar purpose. When we're thinking about dinosaurs like Microraptor, though, we have to remember that iridescent coloration actually is not possible for more primitive types of feathers, and this is because when advanced feathers have these kind of hooked barbules that allow them to like zip up to become a flat surface that can be used as an airfoil, they also trap little bubbles of air. And in modern birds, the refraction of light into those bubbles of air is what's responsible for iridescent coloration, as well as blue and green and purple coloration. There is no blue pigment in all of bird feathers. The blue coloration in birds comes entirely from the structural properties of the feather. So this has obvious implications for reconstructing dinosaurs, because if we know that a given dinosaur was extremely unlikely to have these kinds of feathers, then it probably was not able to be green. Now, in the case of green feathers, there is one green pigment that is confined to only 2 families. But for the most part, green coloration also requires structural coloration. So we can also look to the properties of diet that influence the coloration of feathers. And so when we see the bright reds and yellows of birds like canaries and cardinals and tanagers and things like that, that kind of bright yellow, red, and orange coloration requires a molecule called carotenoids. And carotenoids are used to synthesize those pigments. Now, it is only possible to synthesize these types of carotenoids from a plant-based diet or a fruit-based diet. And so this is one way that we can use not only direct evidence of gut contents, but also just the kind of obvious lifestyle that a dinosaur would have been living based on its teeth and its weaponry and so on to infer certain things about its coloration. So a dromaeosaur like Deinonychus, or Utah raptor, was very unlikely to be able to synthesize bright yellow and red pigments because it was almost certainly not eating very much vegetable matter. So Archaeopteryx is an example where we can kind of combine these different sources of inference to come up with a plausible color scheme for the animal. So Archaeopteryx has had a color study conducted on a single covert feather. So the covert feather would have come from this covering of wing feathers here that overlaps the primaries and secondaries. And that color study determined that it was most likely to be black. And so this led to a kind of a paleoart meme where everybody was drawing Archaeopteryx totally solid black. But I prefer to give Archaeopteryx more of a shorebird type coloration because it lived on the shore, right? We know a lot about its environment. It lived on a tropical archipelago. And if you look at modern shorebirds tend to have a similar sort of motifs in their coloration. And most of them are different combinations of black and white and brown and gray. Okay, so that's coloration and feather structure and so on. But now we need to figure out what these animals were actually doing with these structures, right? So for something like Archaeopteryx that may have been flying, it's a little bit more straightforward. But my favorite dinosaur of all time is Deinonychus. And Deinonychus is a very interesting kind of case study for how these different kinds of inference need to be put together to make different inferences about how they would have looked in life. So how did Deinonychus move about in space? How did it use its enormous claws? And what was it doing all those feathers, right? And so, some people might say, well, we don't have direct evidence of feathers in larger dromaeosaurs, only the smaller ones. So maybe Deinonychus was only very lightly feathered, and maybe it didn't have any of these wing feathers at all, right? But we can use a combination of different kinds of inference to conclude that it is actually very unlikely that Deinonychus did not have structures like this on its arms, although the extent of them is up for debate. So how do we know that Deinonychus probably had something that would have looked a little bit like a wing? Well, if we look at the dromaeosaur family tree, we can see a lot of interesting things here. So Microraptor and Sinornithosaurus are related. They're fairly small. Utah raptor and Deinonychus are very large, and they are relatively far removed from these smaller guys over here. But what we can do with this family tree is we can look at the different examples of direct feather evidence for arm feathers that look kind of like a wing. So the basal dromaeosaur genuinelong is known from a fossil that is very well preserved, and it shows these very significant wing feathers on these arms, right? So even though genuinelong was probably too big to fly, it nevertheless had those arm feathers. Sinornithosaurus was a little bit smaller and may have been doing something approximating gliding, but he also had long feathers on his arms. Velociraptor is bigger than either of those two, and even though we don't have direct imprint evidence for feathers in Velociraptor, we do have quill knobs. So one of the specimens of Velociraptor shows these little bumps that are running along the length of the arm. And in modern birds, those bumps are used to anchor primary feathers. So not just, lightweight hair-like filaments, but actual veins, right, for pennaceous feathers. So there's a very good chance that Velociraptor also had these long feathers on the arms. And then, of course, there's Microraptor, which we already know had voluminous arm and hand feathers. So then, of course, the question is, what about Deinonychus? What would a much larger animal like that be doing with big feathers? Well, in more recent years, we have also discovered a much larger type of dromaeosaur called the Cotoraptor that also preserves evidence of quill knobs on the arm. And so if an animal this big had arm feathers, then it would be hard to reason that Deinonychus, which is about half the size, would not have them. It would have had to secondarily lose them through evolution for some other purpose. So Deinonychus is about 3 meters long, and a typical way of reconstructing its wings in paleoart is as follows. He would not have been able to move his wrist in a tight fold like modern birds do, but all of the available evidence suggests that it probably did have long feathers on its arms and hands, just like its relatives. So of course, the question is, with these big claws and these long mobile fingers, wouldn't such a wing get in the way of using them, right? That's usually the most common argument. How would Deinonychus have been able to grasp prey or climb trees or, kill things or hold things with these big wings on his hands? So if we construct the arms of Deinonychus based on phylogenetic logic, then we should expect that this big 3-fingered clawed hand should be covered in a feather plane that maybe would look kind of like this, with a row of secondary feathers on the arm, the lower arm, and a row of primary feathers attaching to the second digit of the claw. The inside of the hand might look something like this. Here you can see a little better the position of the feathers that would be hypothesized to be surrounding these fingers, with the thumb digit fairly mobile. And so how could Deinonychus be using hands for grasping or killing with feathers like this, if it really had them? So this is a seeming contradiction, right? This is the standard way of recreating Deinonychus in paleoart nowadays, and it isn't just a meme, right? But we have to resolve this seeming contradiction, because Deinonychus had these huge weapon-like hands, and then the evidence for wing-like feather coverage from its close relatives. So it just so happens that we actually do have evidence for exactly this resolution. So in 2006, Phil Center did a study on the dromaeosaur Bambiraptor, and he was looking at the range of motion in the arms of Bambiraptor when he noticed something really fascinating. He noticed that the first and the third finger of the hand appeared to actually be opposable, not too unlike our own hands, right? So our thumb is opposable, and Bambiraptor's thumb would have been similarly opposable. And so even though that second digit is long and stiff, that's the digit that the feathers would have attached to based on a wealth of fossil evidence. And so it's easy to imagine that an animal like Deinonychus could have used its hands in a very similar way. So Center found that these feathers on the hand would not have impeded this kind of grasping motion at all. So an animal like Bambiraptor or Deinonychus would have still been able to use its hands for grasping. He also found that Bambiraptor would have been able to navigate a long plane of feathers on his hands to grasp an object close to its chest with one hand at a time. So he reasoned that dromaeosaurs may have actually been able to carry an object like a prey item or a baby away from danger, something like that, by holding it with one hand close to the chest, because the range of motion afforded by dromaeosaur arms would have been able to do that quite easily. And so this, even though Center's studies demonstrated why feathers on the hands of dromaeosaurs would not get in the way, we still need something a little bit more. We need some sign of what good these feathers would have done, right? I mean, they must be there for something. So we also have some information about that. And one such study can look at ontogeny, that is how animals develop over their lifespan. of Deinonychus to propose that maybe it actually did have some partial flight adaptations, at least when it was young. So the example here on the left of these two claws come from two different specimens of Deinonychus, one of which is thought to be a full adult. So that's the MCZ at the top here, and the other of which is thought to be a juvenile, the YPM. So the big thing to notice here is that the juvenile claws are much more strongly curved. And as the animal gets older, the claw straightens out. So why would that happen? I mean, things like this don't happen for no reason in evolution. And so, so Parsons and Parsons had concluded, based on this evidence, that younger Deinonychi might have had some climbing adaptations, and that they could have used these more strongly curved claws to climb up trees and to grasp when perching on a branch, and so on. Because if you look at the claws of modern birds that do a lot of clinging, like woodpeckers, they tend to have much more strongly recurved claws, like the young specimen here. So this is one possible use of such voluminous arm wings in Deinonychus, that maybe when it was young, it would have been able to use them to maybe glide from high surfaces. And as it aged, it would perhaps find less use for them. Or perhaps not. In 2011, Denver Fowler published a comparative morphology study on the feet and ankles of Deinonychus. And what he found is that Deinonychus had extremely short ankles. Now, all dromaeosaurs have somewhat short ankles, but the proportions of the ankles in Deinonychus are extremely similar to the proportion of ankles in birds of prey that are alive today. So based on this and other features of morphology and the grasping motion that would be possible in the feet, Fowler concluded that Deinonychus may have actually used this unusual ankle and foot to kill prey in the same way that hawks and eagles kill prey. So it would have kind of used its weight on top of the prey item and put the center of its weight on the big sickle claw on the inside, and then mantle with the wings over the prey item, just like hawks do. And so Fowler was able to very specifically show evidence, not from just evolution alone, but from actual function, that Deinonychus might have had quite a benefit from these wings, that it used them to stabilize itself for balance, and maybe even engaged in a kind of primitive flight stroke when it is balancing. And so he called this raptor prey restraint, which posited that Deinonychus may have used its strange feathered arms and hands for flapping, grasping, and killing, possibly all at once. And so this is one of my favorite papers in paleontology, because it uses multiple sources of inference to construct a very ecologically plausible role of these different features of anatomy in Deinonychus. So take-home point here is that the strongest sources of the best sources of inference in paleoart often come from different places, and to produce a really rigorous evidence-based reconstruction of a dinosaur engaging in a behavior, you don't need to always be extremely conservative and just follow the fossil exactly as it presents itself. We can use multiple sources from different areas of study, including evolution and phylogenetic bracketing, but also functional morphology and biomechanics, to come up with a truly plausible and realistic construction of a dinosaur. So next, I'll talk about behavioral inference. And so examples like raptor prey restraint kind of straddle the line between form and function and behavior. And that's no coincidence, because most of the time animals use their anatomy to in the service of some kind of behavior. And so figuring out the plausible behaviors for dinosaurs kind of adds an additional layer of complexity to paleoart. There are certain things that we know for sure that dinosaurs, they for sure killed and ate prey. They for sure ran away from larger predators. They definitely engaged in the 4Fs, so the so-called 4Fs that are basically common to all life. But we need to go beyond that and think about what specific iterations of these behaviors are actually plausible, given the evidence and given our ability for inference. And so one of the most common depiction of all types of theropod dinosaurs is in various kinds of aggressive behavior, right? So Deinonychus might have fought with other members of its species. It might have used its wings, its arm wings in the service of balance or longer leaps in order to do so. And it also might have been a fairly generalist predator, like its small cousin Microraptor. And so in paleoart, it's often kind of fun to explore different possibilities that are plausible given the evidence. So I drew Deinonychus crashing into the water and grabbing an eel simply because I thought it was plausible and because I had not seen it done in paleoart before, and I thought it would be a cool thing to depict. And there's not really any evidence that Deinonychus was limited to a single type of prey item, even though it's common to depict it fighting against Tenontosaurus. Now, what about social behavior in dinosaurs? And this has been quite a big topic in Dromaeosaurs specifically. Deinonychus has been depicted in decades of paleoart as a cooperative social hunter, or a pack hunter. And this evidence comes primarily from these fossil sites of a huge Tenontosaurus, which is a big herbivorous dinosaur related to hadrosaurs. Deinonychus was just a fraction of its size and weight. But the skeleton of Tenontosaurus was surrounded by a huge number of shed Deinonychus teeth and skeletal bits from multiple animals. So on that basis, it was kind of just assumed that Deinonychus was cooperatively hunting that Tenontosaurus. And so even though this is kind of a meme to show Deinonychus in groups stalking through the jungle, about to end some poor herbivore's life, I have not been able to avoid the temptation to reconstruct that meme myself. But we should keep in mind that it actually is not really strongly evident, that there are many other explanations for how many teeth of Deinonychus could come into the same area as a Tenontosaurus skeleton. Perhaps they were mobbing it, kind of like gulls do a rotting carcass on the beach, or crocodiles that will mob a gazelle that's straight into the water. That there's no cooperation involved per se, and there's no reason necessarily to infer it. However, there is some modest evidence of true gregarious behavior in Deinonychus's larger cousin Utahraptor, and this comes from one of Jim Kirkland's discoveries of a huge number of different Utahraptor skeletons that had all been buried in the same place. Now, the interesting thing about that is that there are many different ages represented by those skeletons. So, a bunch of adult Utahraptors might have mobbed a single prey item without cooperative behavior, but then why would a tiny baby Utahraptor be present at the same time? Why would a juvenile be present? Why would an extremely old individual also be present? So that is the strongest evidence that I'm aware of to this date that at least some types of dromaeosaurs had some kind of social structure. So when it comes to behavior depictions in paleoart, even though some of the memes are very fun, I would caution against giving into them too much. Instead, think about what would be a plausible behavior that's still semi-speculative. So in the case of dromaeosaurs and related animals, modern bird behavior can often be extremely good for this, as long as we keep in mind the limitations, right? That dinosaurs were not the same as modern birds. So modern birds are often, especially the males, maybe exclusively the males, are sometimes seen trying to attack their reflection in mirrors and windows and so on. So it's plausible to imagine a dromaeosaur, all pumped up by testosterone, getting upset at the sight of his own reflection. So things like that are plausible without straying too far outside of what we actually know. So dromaeosaurs were probably not really as intelligent as a lot of people, thanks to popular culture, have come around to believe. Another thing that paleoart is very good for when it comes to depictions of behavior is to try and use the environment together with the known information about the dinosaur to kind of have a story, to tell a story. So in this case, I painted Ornithomimus and a baby running together in late Cretaceous Hell Creek because the adult and the juvenile were fossilized fairly close together. So it's plausible to imagine that they really were living together as the young matured. Sometimes you can tell a story that is not necessarily a happy one. So this is an illustration of Dakota raptor, the giant raptor with quill knobs that has now killed the Ornithomimus parent. And if you look very closely, you can see that the baby is hiding, still alive. So these kinds of stories might seem, a little bit speculative and frivolous even, but I feel that they can really serve to enrich the public's experience with dinosaurs when they can see these kinds of stories unfolding in a piece of artwork. And as another example, this is, a simple depiction of T-Rex eating some poor ceratopsian rib cage. But you can also get this feeling from it that there's an interaction that's happening, even if it's kind of a little bit distant. So in this case, there are two dromaeosaurs that are waiting for the T-Rex to finish before they move in and provide cleanup, hoping that they can get a little bite. We also have evidence that sauropods, at least certain types of sauropods, live together in age-mixed herds. So that means that rather than having a separate herd for babies and a separate herd for adults, which is the case with some animals, some groups show that sauropod parents may have simultaneously had young of different ages. And so here I tell a little story in a scene where a mother Brachiosaurus is waiting for her smaller baby who has fallen behind. In other cases, we can depict behaviors that are very strongly evidenced from the fossils themselves without any need for speculation. So in this case, we have a specific specimen of a juvenile T-Rex called Jane that has very distinct puncture wounds on the left side of her face and snout. And these puncture wounds perfectly match the size and shape of another juvenile T-Rex's tooth. And so, we can very plausibly imagine that juvenile tyrannosaurs were probably fighting each other. So there's another behavioral story that is, in this case, directly evidenced from the fossils. Okay, so getting a little bit over time here, but I'll kind of wrap up with just a final few words about how paleoart can be used to actually advance the pursuit of knowledge. and is more than just, pretty pictures of dinosaurs. So obviously, as we've discussed, one of the primary goals of paleoart is to communicate the known science and plausible inference about a dinosaur through evidence. But paleoart can also be used to advance knowledge in a different way, not simply by disseminating it to the public, but by actually using principles of inference to make predictions about the world. And in this way, dinosaurs and their appearance in paleoart can actually represent specific hypotheses. So this quote I like by Italian paleontologist Andrea Cow: dinosaurs are not living beings, they are explanations for the fossil record. And this maybe seems like a kind of silly, contentious statement, but there's a sense in which it's absolutely true. Although, of course, the fossils that we have of dinosaurs represent animals that really did live, our conception of a dinosaur at any given time in human history is indeed based on the best hypothesis at the time for how that animal actually looked. So in the case of Microraptor, the data that we have are vast. We have its coloration, we have its feather imprints, we have aerodynamic studies of how it might have used its wings, and so on and so forth. But for many interpretations of dinosaurs are much less straightforward. So paleoart can use these principles to communicate these hypotheses. And if they're informed by things like evolutionary biology, embryology, and many other types of studies, then they can actually be used to kind of capture a given hypothesis that can later be evidenced. And one of my favorite examples of this, and truly this is the core of what I believe is an important purpose of the paleoartist, is the example of William Beebe's Tetrapteryx and and its relevance to the evolution of feathers and flight. So in 1915, William Beebe was studying the embryos of birds, and he noticed that some of them had longer feathers on their legs, and when the embryo matured, the feathers on the legs would eventually go away. Now, at the time, it was not known that it was not known for sure, at least it was not accepted in paleontology, that birds actually evolved directly from dinosaurs. But Beebe had noticed that Archaeopteryx also seemed to have some slightly longer feathers on the legs. So based on this embryological knowledge, he reasoned that there must have been a four-winged transitional stage that ancient ancestors of birds went through before they lost those leg wings. That's because of the logic of how certain features observed in embryos are often relics of their ancestral state. And that was known in 1915, even though the evolution of birds was not yet fully known. So he illustrated his hypothesis of what animal must exist in 1915, and he called it Tetrapteryx. As we know, and sadly, Beebe did not live to see the fruits of his prediction, but such an animal most certainly did exist and was waiting to be discovered in early Cretaceous Chinese rock. And that animal is Microraptor gui. So this animal is extremely similar to this ancestral form that Beebe predicted almost a century earlier. And so in this way, I think this is a great example of how Beebe was kind of the paleoartist that we should all aspire to be in a way. That the lesson we should take from this is that understanding evolutionary principles and their relevance to things like embryology and genetics, morphology, and many other things can actually open the door to make specific predictions about the way that life looked, behaved, moved, and so on in the past. So guided by knowledge and this kind of deductive reasoning process, a paleoartist is not limited just to the bones themselves. but can be an actual active architect in generating hypotheses about what the future will reveal about the past. And so we use these principles of phylogenetic bracketing and parsimony. But there are times where our predictions can be completely violated by extremely unusual, bizarre finds. This is an animal called E. chi. It's a Scansoriopterid. It's a tiny little feathered Maniraptoran. And as you can see from my reconstruction of this in 2013, because we knew that its relatives had feathers extending from the second digit of the hand, it was reasonable to assume that so did this group of animals. But in 2015, E. chi was discovered, and this animal had an entirely new bone sticking out from its wrist that the authors hypothesized actually supported a membrane instead of feathers, like a bat. And so at the time, this was not extremely universally accepted because there's no sign of a membrane, and this bone could have been anything. I mean, it could have been, a discarded bone from another animal, for all we knew. But just a few years later, an unequivocal example of just exactly this type of bat-winged Maniraptoran dinosaur was discovered, called Ambopteryx. And in this case, the actual wing membrane was indeed preserved. So this was a remarkable finding that I don't think even the most brilliant William Beebe could have predicted in his wildest dreams. So we want to strive to communicate the predictions that are afforded to us by evolution and inference. But when our predictions turn out to be wrong, we need to be ready to update our model of how the world actually is. And so this principle in paleoart that I think is an important one to keep in mind is that paleoart is almost always wrong. At any given time, paleoart needs to strive to be the best that it can be based on the known evidence and inference, but that the world is far too strange and bizarre for us to ever be able to get every detail right. And this is kind of a frustrating aspect, but it's also, I think, one of the most exciting and wonderful things about drawing and painting dinosaurs. All right, that's all I have. Thank you so much for listening, and I'm sorry that went a little bit long, but I hope it was fun. And if anybody has questions, I'd be happy to take them.
Well, thank you
I
very
have a
much,
question.
Emily. And I'd like to ask Mark, what's the best way to manage questions on this platform? We've got about 10 minutes for questions, and then we've got a very short report on discovery and publication of a anthodian fish, a spiny shark, in the Silurian nearby. So Mark, what's the best way to do questions?
So if you want to go ahead and unmute yourself to ask a question, or you can put it in the public chat and I can read it off.
I have a question for you.
All right, David.
Hi. It's more of a sidebar. For paleo art, two good books are Gregory S. Paul's Raptors of the World, and also Fujiti's Evolution of Birds.
Yeah, Paul's Predatory Dinosaurs of the World was like one of my foundational readings for getting into the paleo art, so it's highly recommended.
I got a question for you, if you don't mind.
Joseph?
Great talk, by the way. I was just wondering, when you look at modern birds, you have ideas about putting together their artwork. I was always intrigued by scarlet tannage, the males. And, in springtime, they're bright orange, black wings. But from what I understand, that they change color during summertime to green, kind of like a bright green. And I was wondering, did you ever think about something like that when you're when you're putting together like other dinosaur where like springtime or might have been this color, but in the fall might have been color?
Yeah, that's a really great idea. I have depicted sexual dimorphism like we see in tanagers, but I don't think I've ever depicted seasonal changes in plumage. But that's definitely a plausible idea.
Thank you.
Hello, Emily. Bill Parsons here. I loved your talk, and of course, I love your artwork. Can you hear me?
Yes.
Yeah. Okay. This may be a more direct question. Are you going to be at the SVP conference this fall in your hometown there?
I absolutely will, as long as it's actually here. Fingers crossed.
Of course, that's a big if. But,
yeah.
Well, we'll have some things to shock you with when we get there.
Great. I'm excited.
Anyway, thank you much. Thank you very much. Great talk.
Thanks.
I have a question from George that says very interesting. He has a 1966 print of Rudolf Zallinger's 1947 Age of Reptiles. Within a decade, many criticisms began. Do you expect a similar fate for your work? And if so, what assumptions do you think are most vulnerable to change?
That's a great question. I mean, we have to keep in mind with paleo artists of the past, like Zallinger and Charles Knight and many other greats, that they really were revolutionary for their time, and that we have to remember the context of what was known and unknown at the time, and try not to judge them by modern standards. In my own case, I think that it's completely likely that some of my pet hypotheses will be put out of their misery in due time. I'm not sure which of them would be most likely. I think that we will continue to find out some extremely bizarre and unpredictable things about the evolution of feathers in dinosaurs, and which groups of dinosaurs had feathers and did not have feathers. And it's possible that things like the feathered Utah raptor or whatever will someday be shown to be false with skin impressions or something like that. But that's part of being a paleo artist, that you have to steel yourself against that possibility.
There's a comment from David Thompson. Says, of interest, the current issue, February of Natural History, has an article on the 80-year-old Disney movie Fantasia and how this early movie has affected so many of us and was seminal in paleo art.
Yeah.
Yeah, I just thought you might be interested in noting that, because he goes very carefully through the inaccuracies of the Disney thing, but also how it has affected many of us. And I'm sure some of us here who have ever seen it were pretty impressed by it. I know what it did to me when I was 12 years old. So it is quite a piece of art for its time. It was completely inaccurate, but it did have a powerful effect on many of us. So just how art affects people.
Actually, some of the inaccuracies in Fantasia balance each other out to actually produce a more accurate scene. So there's a scene where a T-Rex is battling with a Stegosaurus, and those animals were separated by millions and millions of years. They could not possibly have contacted each other. But the illustrators also gave the T-Rex 3 fingers on his hand. So it turns out that it looks a lot more like Allosaurus than T-Rex, which of course did eat and hunt Stegosaurus. So maybe less inaccurate than some people believe.
Can you hear me?
Glenn, go ahead.
Yeah, it's Glenn Kubin. Great talk. I really enjoyed it. I want to thank Mike for inviting us in the North Coast Fossil Club. We have several members participating. One question I have is, to what extent do you use digital drawing and painting versus conventional methods?
I would say I'm split about 50-50. I do work in digital a lot, but I also really enjoy using gouache. That's my favorite traditional media, and also oil paint and a few other things. But I do get sick of using Photoshop, and I like a break with digital media or traditional media now and then.
Do some of your paintings involve both digital and conventional?
Yes, some of them do. Some of them are heavily modified in Photoshop, I guess I should say, after starting out with gouache. That's fairly common. Yeah.
Do you use any other digital software besides Photoshop?
No, I haven't. I've tried to get into a few in the past, but Photoshop, I've learned all of the tools and the menus and stuff, and it's kind of hard to learn something from scratch. But
right. Okay.
yeah.
Thanks.